Greetings and welcome to Mr. Van Loo's poorly monetized low-budget science channel. Do not click like, do not subscribe. Okay, today we're going to go over topic 10.1, describing fields, and this is the first of 2 lessons. So your learning objectives are to be able to represent sources of mass and charge, lines of electric and gravitational force, as well as field patterns using appropriate symbolism. Next, you'll be able to solve problems involving gravitational and electrical fields. This usually occurs via handout or example problems in your book. Okay, so let's talk about gravitational fields. So a gravitational field around any object with mass will be given by this formula, where G is equal to big G times big M divided by R squared. And of course, all of this is meaningless if we do not define our variables. So it's very important that you are able to do that in your data booklet or elsewhere. So first we have G, small g, being gravitational field strength. The big G is our gravitational constant, and you can find this in your data booklet on the first page at any time, okay? R is the distance to the object with mass. Okay, so we're talking about here then radius. Okay, so the source of our gravitational field is the object with mass m. We'll talk about this in a little more detail here shortly. So first, before then, let's look at a gravitational field around a spherical object, as you can see here. We showed the gravitational field around a spherical object with these radial field lines, okay? And usually when we're talking about gravitational distances, we're talking about center-to-center distances between spherical objects in the case of IB physics. If we were dealing with non-spherical objects, we would need to look at the center of mass, but that is not part of IB physics, so you don't have to worry about it. Nice. Our field lines here are all going to be perpendicular to our surface, the surface of our sphere. And if we then zoom in on the surface of our sphere, we lose the curvature. But our field lines are still perpendicular to the surface. So an easy way to think about this would be to imagine yourself standing on a sports ball field, sports ball of your choice. And to you, that field looks perfectly flat. However, if you zoom out to space, that will look like a very, very tiny part of a sphere. Okay, so this would be the perpendicularity you see on your sports ball field. All right, so then we have gravitational potential energy, and we have this nice little diagram here. You can see our larger object with mass capital M. Our smaller object has a mass of small m. And here we bring our object in from an infinite distance away from the large object. And we move it in from an infinite distance to radius r. Okay? And at this point, at radius r, it experiences gravitational force, which is given by F sub g here in this particular diagram. Okay, so we have our 2 bodies. Yeah, in theory, these bodies will experience gravitational attraction from any point in the universe. So you, right now, are, in theory, gravitationally attracted to everything in the universe, which is pretty cool. TOK question, can we prove this? That's actually not a very good TOK question. It's kind of a yes or no question. But the answer is no, we can't. So if we separate our objects by an infinite distance, the gravitational attraction will be 0. Okay, so we move this out to a point at which our gravitational attraction is 0. That's an infinitely large distance, and that's where we start. Okay. We move the smaller body closer, and in order to do that, we have to do work on this object. So Gravitational potential energy is defined then as the amount of work done to move our two bodies closer together from an infinite distance. And this is very, very important. In fact, the work done will be given by gravitational potential energy is equal to negative large G times large M times small m divided by R. And because our force is changing as the objects come closer, we need calculus in order to derive this formula. And rather than bore you with it, I'm going to leave you to look it up. If you'd like to do that, it's in SOCOS on page 397. Calculus is not required for this course, but it can be helpful when explaining some of our theories. So there you go. The negative sign is going to give us the direction of force here. If this were a positive sign, we would have a repulsive force rather than attractive force. And we will see that when we look at electromagnetism or something similar. And of course, defining our variables, once again, we have m is larger mass, small, large m, larger mass, small m, smaller mass. G is our gravitational constant. R is the distance between objects. Ta-da! All right, so this definition we've already covered. So there it is. You need to put it on a flashcard and memorize it because examiners love to test you on this particular point. So know it, love it, memorize it. This relationship can be expressed in this way, although it loses a lot of context. So it's really important that you associate this definition with this equation, okay? But it is in your data booklet. So the data booklet gives a slightly rearranged version where work is equal to mass times our change in gravitational potential. Ta-da! Okay, so here we have an object moving from position B to position A, or vice versa, doesn't really matter. The key point here is that the amount of work done on the object will be independent of the path taken, and it is scalar, okay? So what matters is the change in potential energy from points A and point B, and that is determined by looking at the distance, the center-to-center distance between our large object and our smaller object at point A, and then our large object and the distance to our object at point B. Okay, and so that change in distance from here to here and from here to here will give us our change in the gravitational field. Okay. Electric field strength is, moving on, sorry. Electric field strength is determined by measuring the force on a test charge. So you might note that it's not irrational then to think of this as a test mass when we're talking about gravitational fields. Perfectly rational way to think about things. So in the case of an electric field, we have our test charges, and you might recall those from topic 5. And electric field strength then is given by the force acting on a test charge, Q. If we substitute coulombic force into this equation, we get this very useful equation, which I've talked about in previous videos, where electric field strength is equal to Coulomb's constant times the charge of the object around which we're trying to measure the electric field, divided by the distance to our test charge squared. And this is review from topic 5, and I don't think I defined those variables, but I just did verbally, so there you go. Oh, there they are. Nice. Okay. See, I did define everything. Yay. All right, so here we're going to look at a couple of test charges here, or not test charges, but a couple of charges right next to each other. And these are what we call a dipole. So a dipole is defined by two equal and opposite charges. And in this case, they're separated by distance A. So the electric field from each charge is shown as a vector at point P. Actually, I've shown a force here, but it's fine. If we imagine that this is a test charge residing here at P, we'd just be looking at the force per charge, and that gives us our electric field. Okay. In order to find our net electric field, we have to add the vectors together. And I have a review here for vector addition, which maybe I will share with you guys in the YouTube world. I also have some videos on this as well. So I'll throw a link up here if I remember. I'll try to remember. Okay, when we're adding these two particular vectors together, it's a little bit easier because our horizontal components of each vector will cancel out because the magnitude of these vectors is equal due to the magnitude of these charges being equal and the fact that they are equidistant from point P. So what we get then is a net force or electric field in this direction, pointing downward. Oh, an unanimated slide. So shameful, Mr. Van Loo. Okay, here we see electric potential energy, and this is going to be similar to gravitational potential energy. So we move a test charge from an infinite distance into point P. And what we find then is that the electric potential at point P is work done per unit charge and bringing a small positive test charge, Q, from infinity to point P. And again, you must memorize this definition. Fortunately, it's quite similar to our gravitational definition. Okay, so our electric potential can be expressed, no surprise, as the work done per charge. Again, this is the work done moving our charge from an infinite distance into a larger charged object. Okay, our data booklet then gives this version, once again, where work is equal to charge times our change in electric potential. Okay, once again, electric potential will vary by the distance between the objects, where electric potential is equal to Coulomb's constant times the charge of the larger object about which we are trying to measure the field divided by distance between the two objects. Okay, so we can relate changes in work and electric potential energy to radius. This is also applicable for gravitational potential energy, although of course we have different values here. What we're going to find then is that changes in potential energy are equal to a change in work, which makes sense. The unit for both is joules. And this then will be equal to Coulomb's constant times the large charge times the charge of our test charge or test object divided by a change in radius. So Coulomb's constant and the charges of the bodies remain constant, which means that our change in work or change in the potential energy are inversely proportional to our change in radius, change in distance between the objects. Okay, so here, once again, we're moving a charge from point B to point A. And once again, the path taken does not matter. We're only concerned about the distance between point A and our larger charged object, and the distance between point B and our larger charged object. Okay. Electric potential in this circumstance is scalar. So we can just add electric potential from each object to find our total electric potential at a point P. And that will look like this, where our total electric potential is equal to KQ sub 1 divided by R sub 1 plus KQ sub 2 divided by R sub 2. Note that we could have negative signs on either Q1 or Q2, and that will change the sign of our terms. So you need to be a little bit careful about that. Okay, finally, we're looking at an electric potential surface here. Here we have a map of electric potential on a plane. And what we see here is a high point showing a positive charge and a negative point showing a negative charge. And you may also see a similar map for gravitational potential. And a map for gravitational potential would only be divoted because there's no positive gravitational force. It's always negative, showing attraction. Right. Okay, finally, last but not least, here we have a diagram showing the electric potential of a positively charged sphere of radius r. We have this interesting scenario where the electric potential inside the sphere is constant throughout the entire sphere. That's what this flat line is telling us. The reason for that requires calculus to explain, but it's because the vector sum of all of the forces on a test charge inside the sphere would be the same everywhere inside the sphere, which is pretty cool. So constant electric field and electric potential inside the sphere. Awesome. Once we get outside the sphere, however, our electric potential is going to decrease inversely with distance. Good times, good times. So yeah, when you go to university, you can expect a lot more fun with this kind of stuff if you take electrostatics. And also note that a sphere, because we expect the charges to distribute evenly across the surface, makes this quite easy to deal with. If you end up with non-spherical objects, things get quite messy very quickly. Okay, if we have a negatively charged sphere, we just mirror our previous image across the x-axis, and it's the same thing. And that's it. Okay, so here's your checkout. Now you should be able to do these things. What I recommend you do is work on some example problems involving gravitational electric fields. Perhaps one day I will put up a video including some example problems as well. Additionally, my sources for this presentation are from the Excellent Physics for the IB Diploma by Kay Tsokos, and I used Google Slides LaTeX and Adobe Illustrator in here as well. How could I forget? Okay, thanks for watching. Have a great day. Do not click like, do not subscribe, and take care.